software projects. It just feels like a universal truth, doesn't it?
Yeah.
You know, the delays, budget spiraling, the sheer struggle to build complex stuff that actually works right. You've probably seen it, maybe lived through it yourself.
Oh, yeah. It's a challenge that's been with us pretty much since serious software development began, long before the tools and tech we have now.
And what's really amazing is that decades ago, someone was like wrestling with these exact same issues, managing this massive complex build, and they wrote it all down. Lessons learned the hard way in a book that became, well, essential reading.
Absolutely. We're talking Frederick Brooks Jr. and his classic, The Mythical Man Month.
So this deep dive, we're going to pull out some of the really powerful insights from excerpts of that book. It's based on his time leading IBM's huge operating system 360 project back in the 60s. But crucially, he also revisited it 20 years later, reflecting on, what held up and maybe where he got things wrong.
Yeah, our mission today is to really dig into those fundamental kind of persistent challenges Brooks saw in software engineering, project management too. We want to understand why they still feel so relevant and what lasting wisdom and maybe some surprising angles this book offers you. It doesn't matter if you build software or just manage complex creative work.
Right. It gets a bit technical, sure, but Brooks was great with analogies, making it relatable, and we'll help connect those historical insights to, the world you're dealing with today.
Okay, yeah, let's get into it.
So where does Brooks even start? It's maybe a bit surprising. He talks about the fun of programming first.
He does. He really frames it as something fundamentally enjoyable. It taps into like deep creative urges. There's just the pure satisfaction of making things.
Yeah, that feeling when code finally clicks and does what you want.
Exactly. And not just making things, but making stuff that's actually useful for people. That sense of, impact.
That's definitely a big driver.
And then there's the intellectual buzz of building these incredibly complex structures. They're not physical. They're systems of pure thought, right? These intricate interlocking parts that somehow work. It's like shaping logic itself.
Pure thought stuff. I love that phrase he uses.
Yeah.
Really captures that kind of almost magical feeling, creating something from, well, nothing tangible.
It really does. And it's always learning, right? Every project, every problem, you pick up something new.
Okay, so there are these definite joys, but then right away, he hits you with the inherent woes. What makes it so tough?
Well, the biggest one, he argues, is this absolute need for perfection. Software, unlike, a lot of other creative work, it has to be exactly right for the machine. One tiny typo, a misplaced semicolon.
And boom, the whole thing falls over.
Yeah, the whole system fails. That painstaking effort needing zero defects, it's mentally taxing.
It's a level of precision most fields just don't demand.
And then there's dependency. You're often building on hardware or other software bits that you don't directly control, so your responsibility to deliver is often way bigger than your actual authority over all the parts. Though he does add that real authority, you often earn it through competence, through getting stuff done.
Right, earning trust by delivering.
Precisely. And finally, even with all the creativity, there are always these long stretches of just tedious work grinding through debugging the repetitive stuff that just, has to happen.
Which I guess leads straight to maybe his most famous point about programmers themselves.
Yeah.
They're natural optimists.
Yeah.
Like incurable optimists.
Yeah, maybe only an optimist could survive those woes. You kind of have to believe you can beat the perfection demand, the dependencies, the sheer drudgery sometimes. The classic lines he mentions are, this time it'll definitely run, or the all-time favorite, I just found the last bug.
Oh, we've all been there. Said that exact thing. So we're all those optimists. And that optimism, while maybe needed for resilience, it's the direct cause of constantly underestimating how long projects will actually take.
Which perfectly sets up the most famous principle in the book, Brooks's Law.
Yes. The one line every software manager needs tattooed somewhere.
Adding manpower to a late software project makes it later.
It just sounds so wrong on the surface, doesn't it? You're late, too much work, so you add more people to speed things up. That's the logical step, right? But Brooks says, nope, fundamentally flawed for software.
And the crucial part is why it hurts. When you add people, the communication overhead just explodes. He uses the math. N people means roughly n squared potential communication links. Add more bodies. And the time spent talking, coordinating, explaining, fixing misunderstandings, it just skyrockets.
So whatever you gain in raw coding hours gets eaten up, and then some, by the extra complexity of just keeping everyone synced up.
Exactly. Plus, you disrupt the people already working because you have to redivide the tasks to fit the new folks in, and then you have to train the new people, which pulls experienced folks away from actually doing productive work.
It's like if your house build is behind schedule and you suddenly bring in 10 new builders who haven't seen the plans, don't know the site, and the original crew has to stop hammering to show them where everything is.
It's a really similar dynamic. And late in a project, especially during system testing when it's all supposed to come together, adding people is particularly bad. That stage is highly sequential. One bit needs to work before you can really test the next. And the cost per day is highest because you've got the maximum number of people trying to coordinate.
Okay, okay. So pouring more people onto working project. Just add fuel to the fire. Got it.
Yeah.
Let's shift gears then from people and time to actually designing the system. Brooks puts massive weight on, what was it?
Conceptual integrity. He calls it the single most important thing in system design. He uses this great analogy, contrasting it with European cathedrals built over centuries, by different architects with different styles. He finds them lacking in, unity compared to a single, coherent architectural vision.
So the strong, unified concept for the whole system is way more important than just cramming in every cool feature people think of.
Absolutely. The idea is, without that single vision, the system just becomes a mess. A patchwork quilt, hard to understand, hard to use, full of weird inconsistencies. And the way to get that integrity, he argues, is the design has to come from one mind or maybe a very small group who are just totally in sync.
That feels almost radical now, with all the emphasis on collaboration, but I definitely see the point about avoiding that design by committee mush.
He also pushes hard for separating the architecture that's defining the user interface, the external specs, what the system does and looks like from the outside, separating that from the implementation, which is actually building the code. The architect, in his view, is like the user's agent inside the dev team, protecting that external view.
So the architect isn't just the best coder, they're the champion for the user experience and the system's overall coherence.
Precisely. And here's a neat point. He argues that discipline, constraints, they're actually good for art, for design. Limitations can spark creativity. He gives the example of budget limits on IBM's smaller System 360 Model 30 actually forcing good architectural choices that helped the bigger Model 75.
Right. Sometimes being forced into simplicity makes things more elegant.
Yeah, and it means you have to be willing to leave out good ideas if they just don't fit the core concept. That's a tough call for any designer. Speaking of adding things, there's the famous second system effect.
Ah, yeah. The temptation, when you build the next system, to put in all the cool stuff you couldn't fit into the first one.
Exactly that. The first system, often built under pressure or with new tech, forces some discipline. But by the second one, you've got experience, you've got all these pent-up ideas, you're eager to show off everything you learned. The danger is you over-engineer it, cram it full of features that weren't really essential, making it complex, late, maybe buggy. He even says OS 360 itself arguably suffered from this.
So that hard-won experience can actually backfire if you're not careful.
Without discipline, yeah. Brooks suggests simple things like setting explicit size and speed budgets for functions just to keep that second system enthusiasm contained.
Which links nicely to another really practical bit of advice. Plan to throw one away.
Yeah, this is an analogy from chemical engineering, I think. You don't just scale up a lab experiment straight to a giant factory. You build a pilot plant first, right? To figure out all the unexpected problems, the kinks, the things that don't scale.
And the first software system you build, especially with new technology or concepts, is often like that pilot plant.
It's the one where you find the flaws in the architecture, the performance issues, the awkward user interactions you didn't see coming. It's often barely usable, really. He argues a discard and redesign phase is pretty much always needed. The real pain, he says, is when you're forced to ship that throwaway version to users just to meet a deadline or buy some time. It just causes agony for everyone and crashes the product's reputation early on.
So basically, except that version 1 is often just a learning exercise, an internal prototype, and don't inflict it on paying customers.
That's the ideal, yeah. And because requirements always change, you absolutely have to design the system for change. That means using techniques like careful modularization, breaking it into independent bits, defining really clear interfaces between those bits, good documentation, using higher level languages, and taking advantage of things like compile time operations.
Basically making it easier to update or swap out pieces later without the whole thing collapsing.
Exactly. And even simple stuff like formally numbering releases V1, V2, V3 helps manage that constant flow of change, gives you clear points where the system is stable.
Okay, so we've covered the joys, the woes, scheduling pitfalls, designing for integrity and change. How do you actually organize the people to build it? And how do they communicate effectively?
Brooks really looks at organization through the lens of reducing how much communication and coordination you need. Division of labor, specialization, it's all about letting people work in parallel without constantly having to interrupt each other.
Less talking, more coding.
Well, ideally. And he points out two really key leadership roles that have to exist, often held by different people, especially as projects get bigger.
The producer and the technical director or architect?
Right. Distinct roles, different skills needed. The producer is like the project manager, outward facing.
Hmm.
They build the team, carve up the work, set the schedule, get resources, handle cons with clients or other groups, and ultimately they make sure the thing ships on time.
They're focused on the delivery, the logistics.
Yep. The technical director or architect, that's the internal role, focus purely on the technical vision. They dream up the design, break it down, define that external view we talked about, sketch the internal structure, make sure the whole thing holds together conceptually, solve the really hard tech problems, and manage the communication inside the tech team about the design itself.
And Brooks says it's pretty rare to find someone who's brilliant at both. You need that dedicated technical lead.
He tells this amazing story about E.H. Harriman, the railroad guy, hiring someone named Walter Berkeley just to manage everything for his chief engineer, C.H. Coster, while Coster was building this complex railway section. Berkeley was Coster's slave and Lord High, everything else, handling all the admin, even writing down Coster's technical decisions so Coster didn't have to break his focus.
Wow, that's quite a way to shield the technical lead.
It really separates the craft from the management burden. And building on that idea of focusing the core technical work, Brooks introduces the surgical team model.
Right, this is where you have a small team centered around one top-notch chief programmer, the surgeon, who handles a key piece of the system.
Yeah, the idea is the surgeon does the main design, writes the most critical code, does key testing. They hold that single vision. Then you have supporting roles, maybe a toolsmith, making sure they have the best build and debug tools, a tester focused just on devising test cases, maybe a language lawyer who's mastered all the quirks of the programming language. They all provide leverage for the surgeon.
So you get the design integrity from one sharp mind, but boosted by a skilled support team, and it drastically cuts down the communication lines compared to a bigger, flatter team.
Exactly. It's about maximizing the output of your very best people. Shifting to communication more broadly, Brooks has this thing called the documentary hypothesis.
The idea that no matter your process, there's always a core set of documents that become absolutely critical for managing the project.
Things like objectives, product specifications, the schedule, the budget, org charts, and really importantly, interface definitions. These docs aren't just red tape, they're tools. They force clear thinking, capture decisions, focus discussions, and act as status checkpoints.
And since technical docs often live on for a long time, maybe ending up in user manuals or maintenance guides, getting that structure right early really matters, which leads him to the project workbook idea.
Think of it like the single central place for all the project documents. The key things are it needs to be updated promptly, changes have to be clearly marked, he mentions change bars in the margin, and you need summaries of what's changed. He points out how electronic workbooks finally made this truly practical compared to paper or microfiche back then.
Right, having that one accessible, up-to-date source of truth just makes coordination so much easier.
Totally. Now, for defining the design itself, he says you need both formal definitions for precision and prose definitions to explain the why and give humans context.
You need the nitty-gritty detail, but also the story behind it.
Yes. And he has this great line, never go to sea with 2 chronometers, take 1 or 3. Meaning, if you have a formal spec and a prose description, one has to be the absolute standard. You can't let them drift apart.
And using the actual running code as the definition is risky, right? Because people start relying on accidental behaviors, quirks that weren't intended, and it locks down the architecture too much.
Yeah, exactly. A clever trick he mentions is embedding declarations like data structure definitions or interface specs right into the source code using compile time stuff like macros or includes. That way, the official definition of an interface is literally part of the code everyone uses and compiles.
So the definition travels with the code. Smart.
Very. Lastly, on communication structure, he talks about meetings. Regular meetings with architects, implementers, maybe even marketing folks are needed to surface issues and propose changes. But, and this is key, he stresses that one person, usually the chief architect, needs the final say to prevent endless debate and design by committee fuzziness.
So you vest the power, but it keeps things moving.
It avoids those endless compromises that can just water down the conceptual integrity.
Okay, we've designed it, organized the team, set up communication. Now, the really messy part, actually building and debugging the thing.
Yeah, this is where the rubber hits the road. And Brooks has some hard-won insights here, too. He really stresses the need for sharp tools.
Good tools just make everything easier, faster.
Absolutely. He specifically calls out text editors just being able to manipulate code efficiently. And crucially, building performance simulators early in the process and actually listening to what they tell you. Don't wait until the whole system is built to discover it's way too slow.
Yeah, that's a mistake you really don't want to make. Very costly.
It is. He also talks about scheduling machine time, which was a huge bottleneck back in the 60s with limited mainframe access. He noticed this weird pattern where demand starts low, then suddenly everyone needs the machine right now.
The crunch time.
Right. And his experience showed that giving machine time to teams in big, solid blocks was way more productive than trying to ration it out in tiny slices. Even if the overall machine utilization number looked slightly lower, letting teams focus intensely during their block really boosted their productivity.
Sustained focus beats fragmented time. Makes total sense.
Moving to debugging itself, he argues that conceptual integrity in the design phase actually prevents bugs later on, especially those nasty integration bugs where different parts make wrong assumptions about each other. Clear function definitions, good specifications, that's your first line of defense.
Design the bugs out before you even write them.
That's the goal. And he strongly recommends testing the specification itself early on, preferably by people outside the core development team. Developers, he says, are so deep in the code, they'll unconsciously invent ways to make things work, even if the spec is vague or missing something. An outsider tests the written word, not the developer's intention.
That's a really key insight. Test the plan, not just the thing you built based on the plan.
He also champions top-down design, a concept formalized by Nicholas Worth. You break the system down, layer by layer, from high-level architecture to the detailed implementation. This clarifies the structure, helps divide work into modules, lets you ignore low-level details until needed, and importantly, lets you test things at the right level of abstraction much earlier.
Building the skeleton before you flesh it out.
Right. For debugging individual bits of code, he kind of traces the history from painful manual debugging on the machine to analyzing memory dumps to the interactive tools we have today. But even with interactive debuggers, he notes that planning your debugging session before you dive in usually works best. He mentions studies showing the first interaction you have in a debugging session is often the most revealing.
Basically, stop and think before you start randomly changing things and hitting run.
Exactly. System debugging, though pulling all the pieces together, that's notoriously tough and almost always takes longer than anyone expects. It needs a really systematic approach.
And this is where that termites, not tornadoes idea fits in, right? Schedule slip isn't usually one big disaster. It's a tiny bit of delay day after day.
That applies broadly to managing the schedule, yeah, which we'll touch on more. For system debugging specifically, he advises building lots of scaffolding, dummy components, test drivers, small test files, just for testing. He says it's not crazy for maybe half your total code to be just test scaffolding.
Half. Wow, that sounds like a lot. I guess you need it to isolate where the problems really are.
You need that infrastructure to test pieces on their own before you connect them. And his absolutely critical advice here, add components to the system one at a time. Integrate a piece. Test it thoroughly, including regression tests to make sure you didn't break something that used to work. Then add the next piece. Don't just dump everything together at the very end and cross your fingers.
Incremental integration. Constant testing. Sounds familiar.
Which leads us right back to schedule management and what he calls hatching a catastrophe. That disaster isn't a sudden tornado. It's the slow, relentless damage from termites, those little daily slips. Someone's out sick, a dependency's a day late, a test machine went down.
Those little things that push the deadline back. Just one more day.
He talks about estimating studies showing estimates tend to be sticky. If you overestimate early, you might adjust down later. But underestimates, they often don't change until it's really late in the game, maybe just weeks before the original deadline.
Ouch. So you don't realize how far behind you are until it's almost too late to do much about it.
And constant schedule slip is just brutal for team morale. Brooks really emphasizes that sharp milestones, clear dates, when specific demonstrable things must be done, are actually a good thing for the team. Fuzzy goals just lead to this endless demoralizing grind.
And the PERT chart showing dependencies helps here.
Yeah, it helps cut through that classic excuse. My part's late, but hey, so is theirs. The PERT chart shows the critical path which tasks are actually gating the whole project. Managers need honest status reports, and crucially, they need to foster an environment where people feel safe reporting bad news, reporting slips early, without facing immediate panic or blame.
That definitely requires trust and maturity from everyone involved.
It does. So, after going through all that, the nature of software design, organizing, building, scheduling Brooks pivots to his most famous essay, written much later, No Silver Bullet.
Right. The argument that there's no single magic trick, no technology or technique that's suddenly going to make software development 10 times more productive.
He draws this really key distinction between the essential difficulties, the inherent complexity in figuring out the conceptual structure of the software itself, and the accidental difficulties, the problems caused by our tools, our programming languages, the machines we use.
And his point is that most of the big productivity gains up to that point had come from solving those accidental problems, like moving from clunky assembly language to higher level languages.
But the core essential difficulties, he says, those don't really change.
And what are those fundamental, unchanging things that make software inherently hard?
He lists four main ones. Complexity, unlike building cars, say no two software parts are ever exactly alike. It's intricate, often arbitrary. Conformity. Software constantly has to bend to fit external things, operating systems, hardware, standards, laws, user expectations, all of which change. Changeability. Everyone expects software to be easily adaptable and constantly evolving. And invisibility. Software just doesn't have a natural geometric representation. You can't draw a blueprint of a large system easily. It's hard to visualize its structure.
Right, you can't really see it or map it onto physical space easily.
Exactly. And because these core difficulties are essential, part of the very nature of software, he concludes there isn't going to be any single technology or management technique, no silver bullet that solves an accidental problem and gives us an order of magnitude productivity boost within, say, a decade.
That sounds pretty downbeat.
Brooks insists he's not being pessimistic. He believes progress happens, absolutely, but it comes from discipline, hard work, from incremental improvements on many fronts, not from waiting for one magical fix. He looked at various things being hyped as potential silver bullets back then: ADA, object-oriented programming, AI, automatic programming, visual programming, formal verification, and basically said, yeah, these are valuable, they help, but they're not revolutionary game changers like, say, the invention of compilers was.
He still comes back to the idea that great designs come from great designers, and the difference between a truly great designer and an average one can be huge, like close to that order of magnitude in productivity and quality.
Okay, so let's jump forward 2 decades from when the main book came out. Brooks added these reflections looking back. What did he learn? What did he admit he got wrong?
Yeah, he's pretty candid about it, isn't he?
He is. First, he clarifies that second system effect. The really dangerous one is the second system you actually release to the world. The plan to throw one away advice. Maybe poorly worded. It should have been more like plan for the second attempt at building the first system you release, recognizing that your initial design and build are often effectively prototypes that need serious rethinking or rebuilding.
So it's not about shipping 2 distinct systems, but planning for a major redesign cycle within the development of the first real product.
Exactly. And he makes a really significant admission. He was wrong about David Parnas's principle of information hiding. Back in the OS 360 days, they had a very open approach. Everyone could see everything via the project workbook. Parnas argued for modules that strictly hide their internal workings, their data, only showing well-defined interfaces.
Like a black box, right? You know the inputs and outputs, the controls, but you don't need to know or shouldn't know exactly how it works inside.
Precisely. Brooks comes around completely and says Parnas was absolutely right. Encapsulation, information hiding, they're fundamental for managing complexity. They let you change the insides of a module without breaking everything else, as long as the interface stays stable. He points out this idea is basically a precursor to object-oriented programming.
That's a pretty big shift on a core design philosophy.
It is. He also doubles down on the no silver bullet conclusion. The essential difficulties are still there. But he does update his thinking on how we can lessen their impact. He points specifically to building software using bigger, pre-built chunks, essentially, reusing existing complex components so you don't have to build them from scratch.
Reusability became a much bigger focus.
He also praises the window icon menu pointer WIMP interface as just a brilliant example of conceptual integrity in design, all built around that desktop metaphor.
The graphical interfaces we all take for granted now.
Yeah, he admired how it balanced power and ease of use. Simple ways for beginners, but also keyboard shortcuts and things for experts, letting people learn incrementally.
He also pretty explicitly throws the classic waterfall model under the bus.
Yeah, he says plan to throw one away might have accidentally reinforced that idea of a strict linear process requirements, then design, then implement, then test, then release, which, he says, is just flawed. It assumes you can get the design perfect up front, and that mistakes only creep in later.
Which, as anyone who's built software knows, is just not how it works.
Not at all. So instead, he strongly advocates for incremental development.
Building the system bit by bit, starting with a working skeleton and adding features piece by piece.
Exactly. The key idea is that at every stage, you have a running testable system. You add a feature or a module, you integrate it, you test it thoroughly, including those regression tests, and then you move on. It brings integration problems to the surface way earlier and gives you constant feedback. Rapid prototyping is related, quickly mocking things up. But Brooks stresses the value of incrementally building the actual system you intend to ship.
So build, test, integrate constantly. Don't wait for a big bang integration at the end.
Right. He also flags a couple of unexpected revolutions that happened in those 20 years that did really change development practice, even if they weren't silver bullets for the essential complexity.
Right, quite.
Well, the biggest was just the sheer number and power of personal computers. Suddenly, you had millions of developers with fast machines on their desks, quick compile times, lots of memory for tools, networks for sharing files. That completely changed the landscape from the slow batch processing world of the 1960s.
Yeah, development got way more interactive, immediate.
He also mentions the software industry becoming more specialized, more niche, and this phenomenon he calls the build-on-package approach.
Using things like spreadsheets or word processors, off-the-shelf apps as building blocks.
Exactly. Building new applications by scripting or extending these big, powerful, shrink-wrapped packages, that's a huge way to tackle complexity. You're leveraging massive amounts of already built, tested functionality. Why build your own charting engine if you can just control Excel to do it?
That's a massive productivity boost right there.
Huge. But he points out a problem. These packages often weren't designed to be components. He argues there's a real need for what he calls metaprogramming interfaces, or MPIs basically, documented ways for other programs to control and integrate these big standalone apps, letting a metaprogrammer weave them together into a larger system.
Making standalone apps into true reusable building blocks.
And one last thing, he notes a really positive trend he saw emerging: the empowerment of teams.
Pushing decision-making down to the people actually doing the work.
Yeah, letting individual teams own specific features, manage their own schedules within the bigger picture, maybe even choose their own development processes.
Yeah.
He saw examples at places like Microsoft and IBM and felt it led to better quality, better productivity, and higher morale.
Trusting the folks on the ground to figure out the best way to build their part.
Right, moves the decisions closer to the action.
Wow. Okay, so stepping back from all this, from the OS360 trenches to the reflections 20 years on, what are the really big, enduring lessons for someone listening right now?
Well, it's striking how persistent these core lessons from Brooks are. The optimism trap, the comms overhead being way higher than you think, the absolute need for conceptual integrity, the fact that requirements will change, so you have to build for adaptability, the sheer difficulty of debugging. These headaches haven't vanished, even with way better tools.
So understanding Brooks helps you go into complex projects with your eyes open, right? You can anticipate these common failure modes. It helps you question if just adding more people is the answer, why having a strong architect matters so much, why designing for change isn't optional.
Exactly. It shifts your focus maybe from wishing for that silver bullet to applying discipline, clear communication, and these sort of proven principles. It's about managing the complexity because it's inherent, not pretending it doesn't exist.
And it's really fascinating seeing where he was, right on the money from the start, and where he later said, oops, I got that wrong, like about information hiding or ditching the pure waterfall model for incremental builds. That willingness to revise his own thinking based on decades of experience, that's a lesson in itself.
And here's maybe the most interesting takeaway for you listening now. Brooks's fundamental split between essential difficulty, the unavoidable complexity of the problem itself, and accidental difficulty, the extra complexity we add through our tools, our processes, maybe poor design choices, that distinction is incredibly powerful.
So when you're facing some really tough project or challenge, you should ask yourself.
Yeah, ask. How much of this pain is because the problem is just genuinely hard? And how much are we making it harder through unnecessary complexity or fuzzy design vision or bad communication or maybe just clinging to processes that don't fit anymore? Figuring out that difference, that's the first step to applying the right kind of discipline to tackle the essential stuff and maybe, just maybe, getting rid of some of those accidental headaches altogether.